Good evening. Welcome to the Kiggins Theater. This is Science on Tap. We have quite a show here for you tonight. If you've been paying attention to our rolling marquee, you know that you are here for the Big Bang, no longer the beginning with Ethan Siegel, and we are going to get to him. I'm Dr. Jessica Hebert. I am a renal and reproductive physiologist at OHSU, and I will be, thank you. Healthy mamas, healthy babies. That's what we do in the Hebert Lab. And I am your MC for this evening, so let's get started. Are we ready for tonight's speaker? I know, you're all ready to hear something great. There is a great thing that Ethan starts his podcast off with, and he says, the universe is out there waiting for you to discover it. And I'm so excited that so many of you are going to get to discover Ethan tonight, because he's really amazing. He is the Pacific Northwest's favorite astrophysicist and cosmologist. They are different. Does anybody know the difference? Yeah, there's lots of yeses. We know, Jessica. Oh, I know, because I'm smart. So astrophysicist studies the nature of individual bodies, and the cosmologist studies the entire universe. So Ethan is both, because he's amazing. He has spent many years as a professor of physics and astronomy at the University of Portland and Lewis and Clark College, and in 2015 became a full-time and award-winning science communicator, featured in places like The Big Think, Medium, Forbes, The Wall Street Journal, Scientific American, and many more. He's the author of 6 books, 2 of which you can get tonight out at the signing table when we're done. One is Infinite Cosmos, and the other one is his brand new Grand Cosmic Story, published by National Geographic. It is my pleasure to introduce my friend and a wonderful person and a fabulous cosmologist, Dr. Ethan Siegel.
Thank you very much, Dr. Jessica, for that wonderful introduction. And thanks to all of you for coming out tonight. We've got a really, really full house, which I'm really excited to see. So they told me when I was going to give a talk here, they said, give us a title. And I gave them a title, and they were like, give us a better title. Tell us something we won't expect. I was like, well, most people think the Big Bang's the beginning of the universe, and we haven't thought that since the 1970s. And people are like, what? Make that the title. I'm like, okay. So that's what I'm here to tell you today. Yes, you can buy my books, and I hope you do, and I'll sign them for you for free after the show if you do. But Infinite Cosmos was a book National Geographic approached me about and said, hey, we wrote 3 books about the Hubble Space Telescope, and now we've got a new one. We got the James Webb Space Telescope. We need someone to write a book about that. And so they called the people up at Space Telescope Science Institute, and they recommended me. And I was like, I'm going to say yes. I'm going to say yes. And then they said, oh, you did such a good job of working with us. Do you have any other projects we can maybe make a book with? And I said, well, I've been writing a book about telling the history of the universe, where every time you turn the page, you come forward 100 million years in time, where we start before the Big Bang, wind up at the present, and then try in like 5 more pages to tell like the whole history of the future and what it's going to be. And they were like, we can make a book out of that. So that's my newest book. It came out just a few weeks ago, and you're among the first people to have the opportunity to get it here, which is really exciting. But today, I'm going to take you beyond most of what's in the book. We'll talk about some of the things that are in it, but most of it to go all the way back in our quest to find the beginning of the universe. Because for thousands of years, we didn't know at all. All we had were stories that we told each other and things that sounded good and made us feel good. This was a topic for poets, for philosophers, for theologians. And because you came to this talk, what makes me so excited about this is cosmology is no longer the playground of poets and theologians and philosophers. It is where scientists go. We say if we want to know what the universe is like, then what we're going to do is we're going to look to the universe and ask it some key questions and see what are the answers that it gives us. And then we're going to use that to inform the theories we make, the pictures we make, and also what types of next questions we're going to answer after that. So that's what I'm excited to tell you about today. So how did the universe begin? Well, why don't we start here, because this is where we're pretty solid, and we'll try and rewind the clock. Because one of the beautiful things about the universe is when we look out at it, here in this room, we see each other as we are mostly right now. But if we look light years away, or thousands, or millions, or billions of light years away, we're only seeing the light that's arriving now. And that light had to travel years, or thousands, or millions, or billions of years to get here. So when we look farther and farther away into the distant recesses of the universe, we're actually looking back in time at the universe as it was all of those years ago when that light was first emitted. So we could say, all right, here's Earth now, because it's night. Right? This is what Earth looks like from space if you have really good vision and you're standing very far away from it. But if you were looking at Earth, 2 billion years ago, it wouldn't have looked like this at all. It would have looked more like this. Because 2 billion years ago, Earth survived its greatest mass extinction event in history. Because 2-point-something billion years ago, organisms evolved that were able to do something for the first time that was remarkable on this planet. And that thing they were able to do is called photosynthesis. Organisms evolved, and particularly the cyanobacteria in the oceans evolved, where they could take sunlight through a series of molecules and transform it into energy. They could use that energy for their life processes. They could use that energy to create sugars. And as waste products, this is great. This is very important. If anyone needs to get up and leave to have a drink, I will not be offended at all. Remember to support your local bartender. We will be back for more of that. So 2 billion years ago, a little over 2 billion years ago, the oxygen started gradually accumulating and accumulating and accumulating in the atmosphere. And oxygen has this interesting property that it's a corrosive agent. It has this interesting property that, unlike carbon dioxide and methane, it does not trap infrared light. So when our atmosphere went from being dominated by carbon dioxide and methane to being a large presence of oxygen in there, something started to change about the Earth. And in particular, it reached a tipping point, and all of a sudden, it froze. It froze over solid. Earth was a snowball planet, even at the equator, for about 300 million years. So when we talk about searching for life in the universe, everyone says, I want to find an Earth-like planet. And I always try to remind them, but when? Because this is also an Earth-like planet. It's just not like Earth today. So make sure when you hear people talking about, we haven't found any Earth-like planets, well, come on, we were an Earth-like planet for 4.5 billion years. In fact, we can go all the way back. We can all the way back to when it was forming and being an Earth-like planet. And in fact, we've seen plenty of instances of this. We have planets forming around stars right now here in our own galaxy. When you look at the constellation of Orion and you see the Orion Nebula, perfect for this time of year whenever it's clear skies, which is every night in the Pacific Northwest. You can see the Orion Nebula, and inside of it, there are hundreds of new stars that are forming, almost all of which have planets and protoplanetary disks around them. And so you wonder, well, if this is what's going on here in our own backyard, what's happening in those distant galaxies that you see across the universe? Fun fact, before 1923, when we saw these distant spiral-like objects in the sky, nobody knew if they were galaxies or not. In fact, the idea that they were galaxies was only the second leading theory. The first leading theory is, oh, no, these aren't galaxies. These are this thing. These are star systems that are forming, and the spirals you're seeing are the dust around them. And that's what people thought they were. They thought these are things right in our own backyard. These are part of our Milky Way, like everything else. And people argued about it. In fact, in 1920, they had a literal argument over it. The American Physical Society sponsored a debate, and they had big famous astronomer Harlow Shapley come out, and other famous astronomer Heber Curtis come out, and they argued with each other about what are the nature of these objects. And, what I say to that is, yeah, it's great. They had an argument, and it was useless, because we don't settle things in science by arguing over it. We go and get data. We let the universe answer it. If we're arguing over it, well, that means you can make more than one case for something being true. But you go out, you collect the data tells you the answer. And then you don't have to argue, because you don't have to have an opinion. You can just know. That's what we like to do. Boy, doesn't that sound like a fantasy here in 2025? So what did they do? They said, well, the first thing we want to do is we want to measure the distance to these objects. Because if we can measure the distance to the objects, then we can determine, well, if they're maybe 100 light years away or 1,000 or a few thousand light years away, they're probably in our own galaxy. But if they're like millions of light years away, well, none of the stars we found are that far away. It's probably something cosmic, something beyond our own galaxy. So that was one thing we set out to do. We had discovered different types of stars, including stars, as Jessica told you, that we call standard candles, where you observe some property of them and you know intrinsically how bright they are. Like this light shining in my face, which is why I'm not looking directly ahead. If I stared at it, I'd be like, oh, it's what? That's like a 1,000-watt light bulb. But if I know it's a 1,000-watt light bulb, then if I see it and I say, oh, look how bright that thing looks, now I know how far away it is. Because I know intrinsically that's the kind of light bulb it is. Well, stars are like that too. You can observe things about stars, and if you know, oh, I see it's a variable star, and I see how fast it's dimming and brightening and dimming and brightening, now I know how intrinsically bright it is. We'll come back to that. That's the idea. But before that ever happened, back in the 1910s, people were observing different galaxies, or suspected galaxies. We didn't have that word yet because we didn't know. And they said, hey, guess what? If I go and I measure that object, I can see it has the same types of spectral lines that atoms make in the laboratory here on Earth. And if I look at all these different objects, I see they all make those same spectral lines. But can you see that they have little arrows that get larger and larger and larger as we come down? That's because all of these lines, they don't come at the exact same frequencies that they come at here on Earth. They don't have the exact wavelengths. They have wavelengths that are all shifted by a certain factor, like they've been stretched. And there's this idea that maybe some of you will remember from when you're kids and you hear that summer sound, that sweet summer sound of the ice cream truck. If you remember that, you can tell if the ice cream truck is coming towards you or moving away from you, can't you? Just by what frequency Pop Goes the Weasel plays at, right? If you hear that high-pitched, oh my God, give me my 50 cents, I'm going to go out and buy the ice cream, it's coming, it's getting closer. And if you hear it the other way where it's lower pitched, boom, 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 I missed it, I have to wait till tomorrow. Light does the same thing as sound. The farther it's shifted, the longer the waves get stretched to, the faster that object is receding from us. And yes, as Jessica told you, some of them really do look like they recede faster than the speed of light. Good thing for the expanding universe. All right, then 1923 comes along, and this guy, who a pretty famous telescope is named after. This is not James Webb, this is Edwin Hubble. The telescope actually isn't named after him, it's named after the Hubble constant, which is named after him, so it's like his grandson. He was observing this, which I'm sure you can all tell is the Andromeda Galaxy. This is what it looked like through that telescope in 1920. Well, that picture's from 22, this date is from 23. So Hubble's observing this, and he's like, I'm going to look for novae in this nebula to see what's going on. So he found one up there, and he marks it, and he writes N. And then he found a second one over there, and he marks it, and he writes N. And he found another one, and he marks it, and writes N. And then he found a fourth one. And he was so excited, he put his pen down. And he picked up a red pen, and he crossed out the N, and he wrote VAR exclamation point. His successor at this observatory was a man named Walter Baade, and Walter Baade insisted that nobody write on the photographic plates anymore. But Hubble did. Because he was so excited, he realized, look, a nova is when you get a stellar corpse, like a white dwarf, that accretes so much mass that it triggers a nuclear reaction on its surface. This takes time. This takes typically thousands of years. In fact, the fastest recurrent nova we've ever detected in 2025 still takes decades to recharge. When did this one brighten again? Next day, one day. That couldn't have been a nova. He said that must have been a variable star. And therefore, if I know this is a variable star and I know how stars vary, thanks to the work of Henrietta Leavitt, who was the woman Jessica showed you with the "You're Welcome" caption under her, then we know how bright it is. And if you know how intrinsically bright it is, just like that light bulb, then you know how far away it is when you measure how bright it appears. And Hubble said, well, hang on. So I can measure the brightness of individual variable stars in these objects that I now know are their own galaxies. And that lets me measure the distance to them. And then I have the data when I take their spectra that tell me how fast they're moving away from me. And so he said, well, hey, that's a great idea. Why don't I make a graph? And over here on the left is the graph. You can see he measured distance on the x-axis in parsecs, and he doesn't know his units for velocity, so he measures those in kilometers. Per second, Hubble. All right, but you see it makes a line. And then we said, oh, look, here's a modern version of that. All of Hubble's data fits in that first pixel on the graph today. This is how far we've gone. Low redshift stuff, green stuff with the Sloan Digital Sky Survey, yellow stuff with the Supernova Lensing Survey, red stuff with the Hubble Space Telescope. And I'm sorry, I got this graph before they launched James Webb in 2021. But it still works. This was the proof that the universe is expanding, because the farther away you look, the faster the objects appear to recede from us. And this was a key prediction of Einstein's relativity that they made in 1922. People first presented this to Einstein in 1927, and Einstein retorted, well, your math is correct, but your physics is abominable. And George Lemaitre was like, man, Einstein didn't believe me. But it wasn't until Hubble published this in 1929 that people were like, okay, yeah, I guess it really is expanding. And Guess we'll have to stop listening to Al now. But this is interesting because if what this means is the universe is expanding today, sure, it'll keep getting bigger and bigger and bigger into the future. But if we think back to the past, that means things must have been smaller and denser. And also because radiation's energy is defined by its wavelength. If the universe is expanding and stretching the wavelength of light today, that means it's cooling. So if we extrapolate back to the past, when the wavelength was shorter, it was higher energy and hotter. So this leads to a picture where, sure, today we have stars and galaxies separated by vast cosmic distances. But if we go earlier, then we should come to a more primitive universe. And if we go even earlier and earlier and earlier, hey, maybe I can extrapolate all the way back to when time and space and everything in the universe was condensed into a single point. And that's where the idea of the Big Bang first came from. And so scientists, cosmologists, when people were like, okay, maybe you guys are actual scientists and you're not just theologians posing as scientists, started to think about this. We said, well, hey, look, there are lots of different types of energy that you can put in your universe. You can have matter, which I drew with these beautiful black dots in the top, right? That as your universe expands, the number of, say, atoms you have remains the same as the volume increases. So your universe gets less dense. Radiation in the second row is similar. That sure, it also gets less dense, but also because the wavelength stretches, radiation loses energy faster than matter does. Which means if you extrapolate back in time, radiation was more important in the past because things were more energetic. And there's also this type of energy that I have in the bottom that Einstein put into general relativity called a cosmological constant. And this is what happens if space itself has an amount of energy inherent to it. Not zero energy, but some finite positive value. That as the universe expands, it continues to have the same energy density. And some of you are like, yeah, that's crazy. How could that possibly be in our universe? If you've ever heard of dark energy, that's what we think makes up most of the universe today. We discovered it in 1998. It causes the universe's expansion to accelerate. And today we think it makes up about 2/3 of the total energy in the universe, which is pretty exciting. You can only discover most of the universe once. And they did that in our lifetime, which is pretty neat. But we're not going to be talking about the universe today. I want to go back to the beginning, or as close to it as we can get. So you'll say, all right, well, if this Big Bang picture is correct, then that means the galaxies that exist today, they have to be old. They have to be evolved, which means if we look farther and farther away, we should see galaxies as they were when the universe was a lot younger. And maybe they look less evolved, and maybe that means their stars are bluer, and they're smaller in size, and there are more of them. And so let's look, and what did we find? Holy crap, that's exactly what we found. Galaxies today, old, red, big, massive, full of old stars. And as we look younger and younger and younger, we find less evolved galaxies, bluer in color, with younger stars inside, with fewer heavy elements, because fewer generations of stars have lived and died within them. That's pretty consistent. What else do we expect to find? Well, hang on. This is a Hubble era photo. You see Hubble Space Telescope. Boo, we're in the James Webb era now. So what did Webb see? Oh, it took us back even further. And guess what? These beautiful smudges that you see, made out of pixels, these are the earliest galaxies that the JWST is finding. And guess what? It continues. More pristine galaxies earlier in time, closer to the Big Bang than ever before. And it shows us that, yeah, the universe really did evolve exactly as we planned. So then you'd say, well, hang on. If I go back, I should find a time where gravity hasn't had enough time to form galaxies, and maybe there were only the first clusters of stars. And that's a great idea. We've been looking for those. Wouldn't I like to know what the very first stars in the universe were like? What was it like when the universe formed these first pristine stars that have never been part of a star ever before? What's it like? Don't you want to know? Well, this is the farthest object the James Webb Space Telescope has ever seen. It is the mother of all galaxies, and that's why it's named MOMZ14. But it turns out this galaxy is already pretty late. The universe was already 280 million years old, or 2% of its current age, when we see this galaxy. So that's great. If the average human lives to be 100 years, we can hope, right? Then this is like looking at a 2-year-old toddler. But what does an infant look like? What does a newborn look like? What does a baby look like? We don't know. We haven't seen farther than that. This is the limit of what the James Webb Space Telescope can see. So we know, in theory, there must have been stars that formed for the first time, that were pristine, that were made of leftover material from the Big Bang. But we don't know what they are because we haven't found them yet. And even before that, there must have been these dense clumps of matter that were just forming and collapsing and contracting to become the gas clouds that would give rise to stars for the first time. We would love to find those too, but no one has given us a far side of the moon large lunar telescope that they've built in the craters of the moon on the far side so we could look out into the universe with our radio eyes and not have interference from all the radio signals we produce on Earth. If we had a functioning government, we might build one. Maybe someday. We can dream and protest. What about before that? What about before you made these clumps of matter? Well, hang on. I can imagine going back further to when it's denser and even hotter. What about then? Well, maybe at some point in the past, it was too hot to make neutral atoms. If the light's wavelength gets short enough so that the average temperature of the universe was about a toasty 3,000 Kelvin, only half the temperature of the surface of the sun, on average, then that would be the temperature at which the universe wouldn't make neutral atoms because there are enough high-energy photons to ionize them and just make a big ionized plasma. And you can imagine going back before that and saying, well, what if it was hot enough during this really early stage that even an atomic nucleus would get blasted apart by radiation? And you say, hey, wait a minute. Cosmologist, is that just like a religious thing? You guys doing actual science here? Yeah. Eventually, in the 1950s, cosmologists came around and learned nuclear physics too. And when we learned nuclear physics, we said, well, hey, if you had protons and neutrons in the early universe, then maybe you didn't need stars to do nuclear fusion. Maybe things were hot enough and dense enough that you could do nuclear fusion before they were stars. And today we call this science Big Bang nucleosynthesis. And we run these big numerical codes where we say, oh, if you started with just protons and neutrons, guess what? Eventually you would make deuterium. And when the universe cools enough and you have a proton and a neutron fused together, maybe it wouldn't immediately be blasted apart by the high energy radiation. And then you can build your way up and make other things like helium and beryllium and lithium and carbon and boron and, well, I guess only a little of those heavier elements. If I were to sort this by number of atom, it turns out that after the Big Bang, 99.9999991% of the universe was hydrogen or helium. And that tiny little part, that almost a part in a billion that's left over, is mostly lithium. Not a whole lot else. But how do we know this? You said, oh, big deal, Ethan. You do your theory calculations, and who cares, right? That's just pie in the sky. No! We look to the universe and say, confirm this for me. So you find a distant quasar, and you say, hey, guess what? Every time I look at a distant quasar, it doesn't just have emission lines, like the galaxies we looked at earlier did. They also have absorption lines because there's neutral clouds of gas in between them. So you look for the absorption features, and you can look for hydrogen absorption versus deuterium absorption versus lithium absorption, and you can see as you look earlier and earlier, these clouds get more pristine. They have fewer, heavier elements in them, and they allow you to compare what did we predict from the Big Bang versus what do we actually see? And this is consistent with, yeah, there was an early period of nucleosynthesis there. And then you can say, well, hey, let me go look at this leftover glow from the Big Bang. We used to give it such poetic names to things in the universe. Oh my God. This thing that we call the cosmic microwave background today, we used to call it the primeval fireball. We don't name things like we used to. That's a beautiful name. So when we look at this primeval fireball and we look at the fluctuations in there, what are they telling us? Well, they tell us a lot of things, but one big thing they tell us is what is the ratio of all the baryons, which are all the protons and neutrons combined in the universe, compared to the number of photons in the universe, or the radiation left over from the Big Bang. And guess what? If you can measure that, you can make exquisite predictions for how much helium-4, how much deuterium, how much helium-3, how much lithium do you expect to be there today. This one parameter is that baryon to photon ratio on the x-axis. And all these other curves are just determined by nuclear physics. So we can measure from gas clouds how much these element ratios are. We can measure from the microwave background what the element ratios are. And we can calculate from theory what the element ratios should be. This is a huge success. So we come to the Big Bang and we say, what are some key events in the late-time universe? Well, today is 13.8 billion years since the Big Bang. And if we go back to the earliest known galaxy, just skipping 98% of the universe's history, which you can get in my book, I don't skip it there. The earliest known galaxy is just 280 to 285 million years after the Big Bang. First stars, we don't know. We haven't found them yet. We haven't been able to look early enough. According to the best theories and simulations we have, they were significantly earlier, 30 to 100 million years after the Big Bang. Somewhere in there is where we think they formed. Earlier than that, we made neutral atoms, and we see the cosmic microwave background from a time when the universe was just 380,000 years after the Big Bang. What about when we made atomic nuclei? That happened in the first few minutes of the universe after the Big Bang. And I say, okay, but there's more, right? Like, that's great. You told me all this late-time universe stuff, like minutes after the Big Bang. Good job. But what about back here? What about as close to the beginning as we can get? What was that like? Well, we have experiments where we recreate similar conditions, where it was hot and dense, just like it was in those early stages of the Big Bang. We can create a quark-gluon plasma, where instead of having protons and neutrons making up matter, we can make things so hot and dense that we make a quark-gluon plasma instead, where the subatomic particles inside of a proton or neutron are denser and more closely packed together than they can be inside an atomic nucleus. And so you're like, well, that's pretty cool. When did that happen? And we can actually tell. We say, oh, look, by the time the universe is a few minutes old, yeah, we're making atomic nuclei. But back here, when the universe was only a fraction of a millisecond old, we had protons and neutrons. And if I go back even earlier to when the universe was just a microsecond old, then we had a quark-gluon plasma. And so these are other transitions that occurred. And I say, well, what else happened? What else happened even earlier? And we can keep going back. We can say, okay, we go from a quark-gluon plasma to having protons and neutrons. We call that the QCD phase transition. This is when you make protons and neutrons instead of having a quark-gluon plasma. Happens when the universe is maybe 10 microseconds old. Then you say, what about even earlier? And you say, well, we've gone earlier. And we know about the electroweak symmetry, where you make the Higgs boson, where particles get mass, where you have these W and Z bosons. That happens when the universe is maybe 1/10 of a nanosecond old. And there are some things that definitely happened in the universe even before then, because if it happened after that, we would have discovered it. We don't know where dark matter came from, but we know we have it. We don't know baryogenesis, why every galaxy we see in the universe is made of matter and not antimatter. At some point, you had to make a matter-antimatter asymmetry. You had to give the universe a mechanism to make more matter than antimatter. We know some general steps of how that must have happened, but we don't know the exact mechanism for how it happened. And there are other exotic things that should have happened. Many theories predict you would make super heavy particles that could be leftover relics today, that predict the existence of magnetic monopoles, and where are all of those today, that predict all sorts of new phenomena, and we don't see them. And then there was this idea that came along just a tiny, tiny, tiny fraction of a second, something like 10 to the minus 32 seconds of cosmic inflation. And I want to tell you more about this. All right, so if we're thinking about the very early universe, you can imagine all of these particles of the standard model, and maybe some even beyond the standard model, that it's hot enough and energetic enough that you can create anything, right? E equals mc squared. If I have enough energy, E, then I can make something like particle-antiparticle pairs of any mass, m, if I have enough energy, because energy and mass are equivalent. So I make these things in the early universe. Imagine some new particle I make. Maybe it's energetic or more energetic as the different lines show. And I make them, and they're in equilibrium. They follow this black curve until now enough of them have annihilated away, and the universe has cooled enough, and I don't have enough energy to make new ones. So I have some leftover particles, and they annihilate until now there are too few of them to find each other. The universe has expanded and cooled too much. They can't find each other. What happens? They're going to be left over. This is the major scenario that people consider when they think, where did dark matter come from? And so this is the leading idea. If you've ever heard of WIMP dark matter, this is the idea of a WIMP. You had the ability to make something at high energies in the early universe, and a little bit of it is left over today. Okay, then what happens? Well, you say, look, if I made all these different particles, everything in the standard model, a whole bunch of it, as it expands and cools, well, most of this stuff is going to find each other and annihilate it away. And the stuff that isn't going to find each other, most of it's just going to decay away until I'm just left with like a little bit of matter and a little bit of antimatter. But that's not the universe we have. We have a universe that's full of matter and has almost no antimatter in it. The universe, if you run the scenario of, well, if I just made everything equal in equal amounts and then I let it expand and cool, what would the density of the universe actually be in terms of particles? And the answer is more than 1/10 billionth less than we have today. So for every 10 billion particles we have now, if the universe didn't have a matter-antimatter asymmetry, there would be less than one particle for every 10 billion we have today. Not so good. So we invent scenarios to say, well, what could have made more matter than antimatter? And you say, well, let's say we made these super heavy particles, x's and y's, and because E equals mc squared, you can make anti-x's and anti-y's. This is a class of super heavy particles known as leptoquarks, which have properties of both quark and leptons, like the electron. So you say, all right, now I want to imagine that they decay. Because that's what happens if you make a heavy, unstable particle. You let it live for a while, and then it lives too long, and it says, it's time to decay now, just like a good old radioactive atom. The thing is, if I have an X, and I say, well, the X can decay to 2 up quarks, or an anti-down quark and a positron, then the anti-X has to have the same anti-decays. Anti-up, and down, regular electron. Same thing for the Y's. If a Y can decay to an anti-up and an anti-down, or an up and an electron, then an anti-Y can decay to an up and a down, and an anti-up and a positron. But what doesn't have to be the same is what we call these branching ratios, the percent that goes to option 1 versus option 2. You see here I have the X's go 50-50, but the anti-X's go 51-49. Same thing with the Y's. I have them go 50-50, but the anti-Y's go 49-51. And if you do that, then for every 100 X anti-X's and every 100 Y anti-Y's you make just a little bit more of the matter than the antimatter. So when all of this stuff annihilates away, you're left with up, down, down. That's a neutron. You're left with up, up, down. That's a proton. You're left with a few extra electrons over the positrons. Something like that must have happened in the past. And then you say, okay, so this must have happened. We don't know how. Science doesn't end. We're still trying to do it. We want to know the answer to where does dark matter come from. We want to know the answer to where does the matter-antimatter asymmetry come from. And of course we want to know, where does the whole universe come from? Yeah, that's great. Today we've got clusters of galaxies, we had stars, we made atoms, atomic nuclei, blah, blah, blah. We made all those other things that we know we had to make. But what about time t equals 0? What about that? Don't we think that's the Big Bang? Don't we think you could just extrapolate back and back and back until all of time and space and the matter and energy and everything is just in one point? Isn't that a singularity, and isn't that where everything comes from? That's what I learned too. And then when I got to grad school in the 2000s, I learned that no one who studies cosmology thought that for like 20 plus years. And now it's 45 years that people haven't thought that. Why doesn't anyone know this? Well, it's because people who do what I do haven't told you enough. So there are some problems, some puzzles with the traditional Big Bang. I can look in this direction for 46 billion light years. And that's true, even though the universe is only 13.8 billion years old, I can see 46 billion light years away in all directions because the universe has expanded faster than light. And so I look over there 46 billion light years away, and I look over there 46 billion light years away, and I see that they're the same temperature. But how did that happen? Right? If I go to that corner of the room, and I go to this corner of the room, and I find that they're the same temperature, I'm not going to be surprised because maybe the air in the room is well mixed. Thank you to everyone wearing a mask. But if I look at the universe 46 billion light years that way, and 46 billion light years that way, there hasn't been time in the expanding universe for that region of space and that region of space to come to thermal equilibrium, to exchange information, to reach the same temperature. That couldn't have happened. That's not thermodynamically possible. So then why? Why is that direction and 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 that direction? Why are they all the same temperature? Also, Jessica told you that the universe is spatially flat. It could have been curved. It could have been positively curved like a sphere. Or it could have been negatively curved like, I probably need salt, like I could say a Pringles chip. That's a good curvature shape because it's curved down in one direction and up in the other. And then you say, but it's not. It's not either of those things. It's completely spatially flat. In fact, we've measured, and to 0.00019, that level, the universe is flat. So it's really flat. Flatter than the flat Earth. I'm just kidding. All right. And finally, if things got infinitely hot and dense, right? We just talked about this. You get as high as you want, as hot as you want, as energetic as you want. Where are all those leftover high-energy relics? Why do I not see magnetic monopoles? Why do I not have relics left over from that early stage in the Big Bang? I don't know. Well, we're going to find out. But also, there's something else that happened in our universe. Our universe is not just randomly filled with galaxies. Our universe has structure to it. It has a large-scale structure to it, and this is also something cosmologists measure. And it turns out you cannot just make the universe by random fluctuations everywhere. You need something to provide seed imperfections so that the overdense regions, the regions that are just slightly a little bit denser than average, will, because of how gravity works, draw more matter into them and grow and form the stars or galaxies or clusters of galaxies or those large cosmic filaments because they drew matter into them over time. And you need these underdense regions that give up their matter to the denser surroundings and grow into these expansive cosmic voids that have no galaxies in them, sometimes for hundreds of millions of light years, like a giant hole in your Swiss cheese. So these are puzzles with the Big Bang. And you know, people noticed these puzzles starting in the late 60s and throughout the early 70s. And in 1979, one of the Princeton astrophysicists, Bob Dickey, is giving lectures, Einstein Day lectures, right? Talking about these puzzles with the Big Bang. And there's a postdoc, a guy who's just finished grad school in the lecture hall, and he's taking notes. And his notebook is actually in the Field Museum now. You can go see it for yourself in Chicago. And in December 1979, he writes in his notebook, for someone who has the messiest office in probably the whole world. His office was voted messiest office in the world in 2005. He has the neatest handwriting. And in this neat handwriting, he writes, spectacular realization. Star, 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 and draws a big box around it. And he says, if the universe underwent a period of supercooled exponential expansion, it can solve all of these problems. And people are like, what does that mean? So he worked it out and he wrote a paper. And this is where the idea of cosmic inflation came from. And the scientist's name is Alan Guth. He's still a professor at MIT. And what Alan Guth said is, okay, instead of being filled with matter or radiation, imagine that the universe was filled with energy inherent to the fabric of space itself. Now, you have a little moment that elapses. And what happens? Well, the universe is going to double. It's going to double in size. It's going to double in length. It's going to double in width. And it's going to double in height. And then that next moment elapses. And again, your universe, now the expanded universe, is going to double and double and double. And then the next moment elapses and it doubles and doubles and doubles again. And if you do this just about 100 times, you can go from something smaller than the Planck length, which is the smallest length scale at which physics makes sense, to something larger than the observable universe. If you ever did that puzzle where you're like, oh, yeah. I'll tell you what, you pay me a penny on the first of the month, and then you pay me 2 pennies on the second, and then 4 pennies on the third, and 8 pennies on the fourth, and so on. Just for 1 month, I'll be good. And then you realize by the time you get to like the 25th that it's more money than exists on planet Earth. You're like, oh, that's exponential growth. It's like the reverse of a student loan payment. So you say, well, hang on. If this universe inflates like this for just a little bit, is it going to solve all my problems? Because imagine I lived in a universe that wasn't flat, like you see in panel A over here. And then I inflate it for a little bit, and it looks like panel B. And then I inflate it for a little bit, and it looks like C. And I inflate it for a little bit, and it looks like D. If you went out into your backyard and someone said to you, measure the curvature of the earth from your own backyard. You know the earth is curved, but your backyard is not big enough for you to detect the earth's curvature on that scale. And maybe the reason our universe looks flat is because it inflated. And when we look at it, all we see is something that looks like D. And maybe it was curved like a sphere, or maybe it was curved like a 4-dimensional Pringles chip, or maybe it was curved in some other weird way, and we don't know because the part we can see looks indistinguishable from flat. What about that puzzle of it's the same temperature there and there and there and everywhere? Well, hang on. If my universe started off like this, in a tiny, tiny region of space, and then it inflated, well, the reason it looks the same in all these different directions now is because that same region of space got stretched, and therefore the universe has the same properties in all those different locations. That could do it. Where did all my high-energy relics go, by the way? You say, well, hang on. You assumed we went up to infinite temperatures. We went up to arbitrarily high temperatures. What if... Sure, maybe we did. Maybe we went up to temperatures, and look at all these green magnetic monopoles I made. Ooh, scary. That would be bad for the universe. That's okay, because if inflation occurs, now the universe is so big. Oh, there's a green dot. There's a green dot. There's one. And there's one in our observable universe. 46 billion light years in radius. That's it. We would have at most one magnetic monopole in the whole universe. Well, that's why we don't see them. And like I said, sure, maybe the universe started like a sphere, and it inflated and inflated and inflated, and now we can't even tell that it's different from flat because it's so big that the part we can see looks indistinguishable from flat. Okay, fine, Ethan, but what about that spectrum of fluctuations? How do you make that? Inflation does that too. It's very specific about how it does that. It says, look, the universe makes quantum fluctuations on tiny, tiny subatomic scales. But if you inflate the universe, then those fluctuations get stretched. And then new fluctuations occur. And as it inflates more, the original fluctuations get stretched to large scales. And then on smaller scales, you have new fluctuations. And on smaller scales, you have new getting stretched fluctuations. And you should even be able to detect fluctuations that are larger than the cosmic horizon, that are larger than the speed of light could have traversed since the Big Bang occurred. We see all of that. It's written in the cosmic microwave background. It's written in the polarization of the cosmic microwave background. And those same seed fluctuations then get imprinted in the large-scale structure of the universe at all cosmic times. This is not, oh, we have a theory and isn't that cool? No, we went out and measured this. You will hear throughout the course of your life lots of claims that people have overthrown some sort of scientific consensus and there's been a revolution. And I will let you know that if you hear that claim, there are just 3 questions you need to ask. The first question is, okay, We had a theory before this that was the theory that everyone accepted. That theory was accepted because it made a bunch of successful predictions. Number one, can your new theory make all of those same successful predictions? Can you replicate the successes, all of the successes of the old theory? Most new theories fail here. End of story. If you can't already succeed where the old theory has succeeded, you don't have a new theory. You have a crackpot idea. Second thing, we know there are gaps in our theory. There are gaps in all theories. There are ranges of validity that outside of it, they don't look valid anymore. So then you ask, can your new theory fix those gaps? Can it explain what the old theory couldn't? Like, why is the universe flat? Why is it the same temperature in all directions? Why are there no leftover high energy relics? If you can do that, then you've got a chance. Because if you can do step one and step two, now you move on to the third question. And the third question is, can you make new predictions that are different from the predictions of the old theory that you can then go out and test and measure? I would not be here talking to you today if inflation hadn't done that. It's done that, in fact, 4 separate times. Yeah, we can go to the next slide. One of the things inflation predicts is that we should be able to make a universe that is spatially flat, but only to somewhere between the 1 part in a million to 1 part in 10,000 level. We hope to someday detect the departures from perfect flatness because inflation predicts that. We know that we should make these seed fluctuations that could get stretched across cosmic scales, but the fluctuations that are on the largest cosmic scales should be just slightly larger by about 3% than the fluctuations on the smallest cosmic scales. We've measured that. That's called the scalar spectral index, and we've measured it to be 0.965, which is not 1, but less by about 3%, 3.5%. You can say there should be fluctuations on all scales, including scales larger than the cosmic horizon. And we've seen that, again, in the polarization data from the cosmic microwave background. And you should see there's a maximum temperature that the universe could have reheated to when cosmic inflation ends and the hot Big Bang begins. When Jessica asked you what's the minimum size the universe could have been after the hot Big Bang, and she said an atom, a pea, a fist, or a human-sized hamster wheel, the original version of that said it didn't have a human-sized hamster wheel. It had a soccer ball instead, because that was the experimental minimum size it could have been in 2019 when I wrote the article that she got that information from. And I had to correct her and say, no, now in 2025, soccer ball is too small. Human-sized hamster ball, which got translated into hamster wheel. It's fine. But the important thing is, this is an experimental question. If you can measure the maximum temperature that the universe could have reached, then that corresponds to a minimum size the universe could have been after the Big Bang before it expanded to its current size we see it at today. So this is where the frontiers are now. We know inflation happened in the beginning, and its fluctuations, its early history led to the cosmic microwave background and the large-scale cosmic web we see today. But there are still things to learn about inflation, like what type of inflation occurred, what were the particular properties it had, and how does that affect the types of outcomes you see in the universe today. So now let me bring you up to our cosmic timeline updated. Yes, the universe had a Big Bang, but that wasn't the beginning. The first thing we can say about the universe is before that Big Bang phase, there was a period of cosmic inflation. It may have lasted for a very long time, but we know it lasted at least 10 to the minus 32 seconds. And then after inflation ended, that energy that was somehow inherent to space got converted into particles, into matter and radiation. That's where we call the hot Big Bang. That's where the Big Bang is, after the end of inflation. If you go, that's not what I heard, I know. I'm trying to fix that. At some point, baryogenesis occurred, and we made more matter than antimatter. At some point, dark matter was generated. It could theoretically have been generated as late as the QCD phase transition, where we made protons and neutrons. That's the specific case of the axion. But dark matter had to have been there by the time the universe was about 10 microseconds old. We know the electroweak symmetry breaks, particles get mass. You don't have to worry about, the protons in your body decaying. We're okay. Protons and neutrons form. The weak interactions freeze out. You get Big Bang nucleosynthesis. You make your first light elements. Matter dominates radiation. Finally, 9,000 years after the Big Bang, radiation is no longer the most important thing in the universe. Then we make neutral atoms. Eventually, matter starts clumping together. And, after tens of millions, maybe 100 million years, now we've got stars in the universe. It's not dark anymore. Then we make galaxies. Hey, look, we found the earliest one that we know of so far, 285 million years after the Big Bang. Universe evolves some more. I've got a book about what happens in those in-between times. Dark energy comes to dominate the expansion of the universe about 6 billion years ago. About 4.5 billion years ago, planet Earth forms. We finally take on our final shape after some sort of smash up runs into us, creates a cloud of debris that quickly forms our moon. And now, 4.5 billion years later, here we are. So, I want you to think, when you think about the beginning of the universe, the hot Big Bang is our cosmic history. From today, 13.8 billion years after the Big Bang, to not all the way back to a singularity, to some limit, to some hot, dense state that was very hot and very dense, but not infinitely hot or infinitely dense. Because to set that up, we needed a period of cosmic inflation where space doubled and doubled and doubled in size again and again and again and again and again in just a tiny fraction of a second. And we see the evidence of that written on the face of the universe today. And I think that's a good place to stop.
One more time for Dr. Ethan Siegel. We are limited on time for questions tonight, but here, real quick, are the rules. 1, keep it short, 1 question per person. Number 2, your question must be a question, or I will get on you like a spider monkey. If we do not get to your question, you can meet with Dr. Siegel at his table outside. Right after we say goodnight, please let Dr. Siegel get escorted to his table where he will be signing books. Get a book, get a question answered. That's a very good deal. All right, please get your hands up if you have questions. First question, where'd you get your kilt?
Oh, first question, where did I get my kilt? This is a utilikilt, but I have an artist who lives in Forks, Washington, who paints them, does the artwork on me. This is my 5th kilt from her, and I love them. I will get a 6th very soon.
First question.
Why does randomness not explain the difference of mass? Why does randomness not account for how matter was more dense in one place and less dense in another and coalesced?
Okay, this is a good question. Randomness, right? You imagine just random fluctuations everywhere. Why does randomness not account for why some places are more dense and some places are less dense? The fluctuations are what we call Gaussian, which means they follow a bell curve, but they are different on large cosmic scales, from intermediate cosmic scales, from small cosmic scales. And that fact tells us it is not scale invariant. And that is the big factor. We said that inflation makes a very specific prediction of an almost but not perfectly scale invariant spectrum. And so when we measured it, starting with the WMAP satellite in the 2000s, and we said, oh, look, it's almost one, but slightly smaller. And we see that large scales have bigger fluctuations, and intermediate scales have slightly smaller, and smaller scales have even smaller fluctuations. That told us, no, they're not completely random. There's a structure to it, and the structure is consistent with what inflation predicts.
Question 2 down over here.
It's a good one.
So you talked about dark matter, but I also hear about dark energy.
Yeah, I hear about dark energy too. There are big questions about dark energy, and there is this idea that maybe if in the inflationary universe you had energy inherent to space and there was a lot of it, and today we have dark energy that's energy inherent to space and there's just a little of it, are these two things related? Could we have had inflation and something transitioned, and now this little bit we have left is dark energy? And there are thousands of models that connect these two things together. They fall generically under an umbrella word called quintessence, which is the old word for the fifth element. So some people think, well, we have 4 fundamental forces: gravity, strong nuclear force, weak nuclear force, and electromagnetism, and maybe whatever inflation and dark energy are this fifth quintessence. So if you want to learn more about it, that's what I'd look into.
Question 3.
Is there any possibility you could put this into a graphic novel presentation?
I am always a big fan of creative ways to tell a story. I have written and published one children's book, and I am currently, that book is called The Littlest Girl Goes Inside an Atom. And I will let you know, here in this room, I have written a draft of a second children's book called The Biggest Boy Becomes a Black Hole. Because why wouldn't the littlest girl have a brother? So it is always possible. I like to write. I like to tell stories. My drawings are mostly for me and my wife because they should not see the light of day beyond that. But if I hooked up with an artist who said, I want to do this, I want to do this with you, yeah, I'm up for projects. What better time to be making creative art than when the whole world is on fire? 4th question.
Yeah, I just had a question going back to Hubble sitting in his wooden chair and comparing his distance to spectral shift. Just how exactly did Hubble determine distance to these objects?
All right, how does Hubble determine the distance to these objects? So let me summarize all of Henrietta Leavitt's life work in 1 minute. So Henrietta Leavitt is an astronomer at the Harvard College Observatory. She is studying a special class of stars called Cepheid variable stars. What Cepheid variables do, they are these luminous blue stars, and they periodically brighten and fainten and brighten and fainten and brighten and fainten, etc. There is a relationship that was not explained at the time between the period of a Cepheid's variability and how intrinsically bright it was. So when you look very far away, you can't know how intrinsically bright that star is. But if you see how fast it's brightening and faintening and brightening and faintening, and you know it's a Cepheid variable star, then you say, oh, well, I see the period, so I know intrinsically how luminous it is, and then I measure its brightness, and that tells me how far away it is. Fun fact, Hubble was actually off by a factor of 2 initially, because what he didn't know, and what Henrietta Leavitt didn't know, is there are 2 classes of Cepheids. And he mixed them together. Oh well. And that's why Hubble said the Andromeda galaxy is only 900,000 light years away. And in reality, it's more like 2.5 million light years away.
Question 5.
Okay, so in the age you mentioned that that 10 to the minus negative 36 number? Where did you get a number like that?
Where do I get a number like 10 to the minus 32 seconds that inflation must have gone on for? Because I assume if you take the maximum temperature the universe could have reheated to, that is the same as the energy scale at which inflation occurred. And the energy scale dictates how fast something would have doubled in size. So that number comes out to be about 10 to the minus 34 to 10 to the minus 35 seconds. And because I want at least 100 doublings to occur to give us the universe we see that appears to have inflated everywhere we can see, I say, well, if you need 100 doublings and it was 10 to the minus 34 seconds, then it has to be 10 to the minus 32 seconds of inflation at least. That is a lower limit. It could have been much longer. It just had to have been at least that long. And that's a frustrating thing, right? Because you want to know where was the beginning, and all I can tell you is, oh, sorry, like I go back to here and the hot big bang, and then before that there was inflation. How much inflation? I don't know, because I'm only sensitive to that last tiny fraction of a second. Everything that happened before that, whatever it imprinted on our universe, it got inflated away. And so we don't see it anymore. And so when you ask me the follow-up question that I'm sure you have, which is, well then, how do we know what happened before inflation? Or how do we know how long inflation happened for? We have to open ourselves up to the very sober possibility that that information may not exist within our universe.
Can you speak to the fact that some of those early galaxies that you talked about, James Webb Space Telescope discovering, like the MOMZ, being much more developed, much larger than the models would predict, and what that means?
Yeah, look at a galaxy like this. Look at that. We have so much information about, we wish we had so much more information about it than we do. But when we look at this, we do see, look, we have models for how structure should form in the universe. And when we look at this, we say, these things are brighter, more abundant, greater in number than our models predict. What is going on? Guess what? Scientists have been worrying about this since the James Webb Space Telescope started taking data. There were two groups of astronomers. One group of astronomers that I like to call idiots were in the camp that said, oh, this broke the universe. No one expected this. And now our whole models of cosmology are broken and useless and bad. And the other group said, no, we are scientists. We want to figure out why it's different than what we expected. And so the scientists who worked on why it was different, they found 4 factors. First one was the fact, as Jessica told you earlier, that the James Webb Space Telescope was kept cleaner than any observatory in history. So it was actually optically overperforming. Okay, that's great. That gives you like a factor of 2 back. But we were off by like a factor of 100, so that doesn't explain it. And then you say, oh, well, what else could it have been? And it turns out, oh, there's another factor. We've been assuming that stars form at some maximum rate and stay there, and that's where the light comes from. But that isn't how stars actually form. Stars astronomically form in bursts. So many of these galaxies, especially the ones that look like just points, those are from galaxies that are actively forming stars in a giant burst right now. So they are brighter than any galaxy that would have gradually formed stars at some rate, because they are forming stars at a much greater rate than that, and that's why they look so bright. That doesn't explain all of it. If you want to close the rest of the gap, you need to remember that some of these objects in the early universe aren't galaxies, they're quasars. They have active supermassive black holes that inject huge amounts of energy into their surrounding material, and that makes these extended, bright sources of light. So a lot of these, what we call little red dot galaxies, are what we call AGN enhanced. They're enhanced by an active supermassive black hole or an active galactic nucleus. So I wouldn't say we've 100% solved the problem, but those 3 factors overwhelmingly make this, oh, it's a factor of 100 different from what we want to, oh, maybe it's like 20% different from what we realized. And that, to me, is much smaller of a problem. So it is something we worry about, but we think we're on to the answer.
Last question.
Last call, lucky number 7.
Hey, so I understand in science and discovery we have to sometimes invent a placeholder in order to explore how that might solve a problem. And I know that from this perspective, dark matter is something we haven't been able to observe, but we believe is there from artifacts of it. So the recent model of the timescape phenomena, I feel like is more elegant in the sense that it uses existing observational phenomena around gravity and how it can lens time and observation in the universe in order to understand the expansion and the continued expansion without the need for dark matter. Do you have a understanding of where it falls between those three questions of new theories that come up and whether it vets through those three questions?
This is the timescape cosmology of David Wiltshire. So David Wiltshire came out with this idea that said, hey, you have this idea of dark matter, but maybe it isn't dark matter. Maybe you just have the gravitational influence of matter is making time run at different rates in different places in the universe. And so what you think you're seeing of these huge clusters of matter and stuff, maybe this is just a region that's billions of years older or younger than the rest of the universe. The problem is we know how gravity works, and we can weigh these clusters, and we can determine their density, and we can determine their overall mass because of gravitational lensing. So when you do that and you ask quantitatively, how much older or younger can these objects be in the universe than 13.8 billion years? The answer is hundreds to thousands of years at most, not billions of years. So the timescape cosmology disagrees with observations by about a factor of 1 million in time. And that's why even though it has appealing aspects to it, it cannot be right. So it fails on the first point of reproducing the universe we have.
For Dr. Siegel. On behalf of Dr. Siegel, the Science on Tap team, the wonderful people at the Kagan's Theater, make sure you tip them. If you want to stay for Back to the Future, get a ticket at the front. We want to thank you for joining Science on Tap because science is for everyone, and tonight it was particularly for you. Come join me if you're getting a pint glass. We'll see you in 2 weeks. Thank you so much. Good night.